Hi ho, hi ho! In this lecture, we will be coming back around to see things we began with, but from a new perspective. We'll begin with our last major test for convergence, the ratio test, which is very much related to geometric series, the first kind of series for which we learn to distinguish convergent series from divergent series. We will then use the ratio test to investigate power series, which is the fancy name for infinite degree polynomials, Taylor series being the prime examples of power series. And we'll finally be able to clear up old mysteries from the very beginning of the chapter about why certain functions are able to be approximated by Taylor polynomials over their entire domains, while for other functions, Taylor polynomials only seem to work on some restricted portion of their domains. Anyway, all this to come, but let's get started with the ratio test. As I said before, it's very much related to geometric series. So let's begin by thinking about geometric series once again. We know that in any geometric series, there is this common multiple, which I was calling R, that we multiply any term by to get to the next term, to get to its successor. And I mentioned long ago that we use R because we're usually thinking of it as a ratio. It's what we have to divide by to get from any term to its predecessor. So we might say that in any geometric series, the term-to-predecessor ratio is a constant, and we've called that constant R. To make sure this is perfectly clear, the general term in a geometric series has the form AR to the n, so its predecessor has the form AR to the n minus 1. Hence, the term-to-predecessor ratio in a geometric series is the ratio of those two forms, which washes out to R. So in all that follows, you should be thinking of the term-to-predecessor ratio, this phrase that I'm going to keep repeating, as representing R, as being a generalization of this familiar R we've been using all the time in geometric series. Now, however, we're going to be using this generalization for series that are not geometric themselves, but which become geometric in the tail when they look more and more and more geometric in the tail. And one of the very first things we learned about infinite series is that if we have a geometric series, if R, that term-to-predecessor ratio, is less than 1, the series converges. If the term-to-predecessor ratio is greater than 1, then the series diverges. And that familiar fact is the basis for the ratio test. The whole idea of the ratio test is that there are certain series which are not geometric, so they do not have a constant term-to-predecessor ratio. But if we go out into the tail of the series, the term-to-predecessor ratio gets closer and closer to a constant. It becomes constant in the limit, and since the limit is where convergence or divergence is determined, we can use the fact that the series is effectively geometric in the tail to determine whether the series converges or diverges. So the ratio test is essentially testing to see whether a series is geometric in the long run. So let me go ahead and state the ratio test. Given a series, sum of a sub n, we will test it for absolute convergence as follows. Well, we know that if we want to test for absolute convergence, we're actually interested in whether this series converges, the series of the absolute values, which I'm writing down here in my customary green scratchwork color. What I want to do is to look at the term-to-predecessor ratio of this series. I'm going to have a statement about it up here. Given our initial series, we're going to test for absolute convergence as follows. Consider its term-to-predecessor ratio in absolute value. And what's that going to look like? That would be the absolute value of its general term over the absolute value of that term's predecessor. But of course, we remember that the quotient of two absolute values is the absolute value of the quotient. Okay, so we've got the term-to-predecessor ratio in absolute value. If our series were geometric, this would be a constant. Presumably it's not geometric, so this in general won't be a constant. But as we said before, maybe in the limit it will approach a constant. So that's what will show up in our test next. Suppose that that term-to-predecessor ratio approaches some value L in the limit. If L is less than 1, well, what do you suppose happens? If L is less than 1, that means that the term-to-predecessor ratio is approaching some constant that's less than 1. That means in the limit, our series looks geometric with that common ratio less than 1, so it's going to converge. And since we're doing everything in absolute value, the series converges absolutely. If that limit is greater than 1, what do you think happens? Well, again, what is L? If L is some number greater than 1, that means that this term-to-predecessor ratio is approaching some number greater than 1 in the limit. That means that in the tail of the series looks like a geometric series with common ratio greater than 1. Well, the tail is where convergence or divergence is determined, so that means that if L is greater than 1, the series diverges. And those are the cases in which the ratio test tells us something definite. Of course, it's possible that if this limit exists, it might be neither less than 1 nor greater than 1. It might be equal to 1. But in that case, the ratio test is inconclusive. And I have an exercise in the book that gives examples to show why that is so. But in these other two cases, we have a definite conclusion. And I think this is a pretty easy test to understand if A, you understand geometric series, and B, you've internalized this idea that the convergence or divergence of a series is determined in the tail. Put those pieces together, and the old ratio test should feel pretty natural. The ratio test tends to be useful when we are testing a series whose general term has either n factorial or x to the n in it, or both for that matter. And in particular, we will see it most frequently when these things show up, as they will naturally in power series, which are really just polynomials of infinite degree. And of course, polynomials are built up from these kinds of things. So we'll be seeing that very soon when we get to power series. But before we look at such infinite degree polynomials, let's just see the ratio test in action in some concrete cases of numerical series. Let's test this series for convergence. Now, the general term here is pretty interesting, because you might say, whoa, the top is exploding, n to the 20th. Even by the time n is 2, you have 2 to the 20th power, which is over 1,000,000. While down here you have 5 squared, which is only 25. Is this a job for the divergence test? Well, it's a good instinct to have the divergence test in the back of your mind, but don't be fooled in this case. Exponential functions always beat power functions in the end. This one gets a big head start in the beginning, but the exponential function will blow it away eventually. So the general term does in fact vanish, and consequently the divergence test is of no use to us. Well, what am I going to do then? Oh, well, I've got n as an exponent. Maybe this ratio test will help us. After all, I said that's one of the two places where it tends to be useful. Let's try it. The term-to-predecessor ratio in absolute value is, well, let's see, the general term is n to the 20th over 5 to the n, and its predecessor, what's that going to be? Well, if the general term is where the index is n, the predecessor is going to be where the index is n minus 1. So we just have to replace n by n minus 1 in each case, and we have n minus 1 to the 20th over 5 to the n minus 1. If we put it into one fraction, we end up with this stuff. And this simplifies pretty nicely. I need a little more room, so that's better. I have n copies of 5 downstairs, but 1 fewer 5 upstairs. So that means all of these 5s cancel with most of the 5s down here, leaving just 1 copy of 5 downstairs, which I'll put down there now. Then I've got n to the 20th divided by n minus 1 to the 20th. Well, we know how exponents work. That's the same as the fraction n over n minus 1 all to the 20th. So let me put that in there too. And I can clean this up even further. The absolute values I can take off here because all of this stuff is positive. So let's do that. And what does the ratio test tell us to do with this thing? Well, this is the term-to-predecessor ratio in absolute value. And now we need to consider its limit as n goes to infinity and see if it is a constant. Well, how about it? The 1/5 just sits there when we take a limit. But this stuff, of course, approaches 1 as n goes to infinity. So that means this whole thing approaches 1 because we've got 1 to the 20th power. So the entire thing approaches 1/5 in the limit. Okay, so what can we conclude from that? Well, this limit is less than 1. So the ratio test tells us that the series must converge absolutely. So let me write that up. This limit is 1/5, which is less than 1. So the series converges absolutely. And again, this makes perfect sense. Just think in your mind what that ratio test is doing. It's essentially comparing it to a geometric series in the tail. What we showed here was that if we take the term-to-predecessor ratio of that series, it gets closer and closer to 1/5 in the limit. That means it looks more and more like a geometric series whose ratio r is 1/5. And of course, such a geometric series converges. So this series converges. And of course it converges absolutely because these are all positive terms to begin with. But I went ahead and put the absolute values on there, at least in the beginning, to remind you of the general procedure for using the ratio test. So as you can see, it's not a hard test to use once you get used to it. Let's do one more numerical example. Let's test this series for convergence. Now this time you might say, oh, it's that 5n that we said blows up so fast. So fast, in fact, that it swamped n to the 20th. And now it's in the numerator. Maybe now I can use the divergence test. Well, no, because factorial growth is even quicker than exponential growth. So the general term still vanishes in this case. But this one is positively crying out for the ratio test. Not only does n appear in an exponent, it appears in a factorial as well. So let's go ahead and apply the ratio test. By the way, before we do so, don't jump the gun and use the ratio test anytime you see n in an exponent. Sometimes there are simpler ways. I mean, if you see something like this, don't say, oh, I remember, he said if n's in the exponent, use the ratio test. No, you're not a robot. Don't think that way. Think about what the series is for a second. This is just a geometric series. Use simple things first. Use the big guns when you need them. But back to the task at hand. This is certainly not a geometric series. But maybe it approaches one in the long run. That's what the ratio test will help us find out. The term-to-predecessor ratio is, in absolute value, well, here's the general term, 5 to the n over n factorial. We're taking the term-to-predecessor ratio. Everywhere we had n before, we're just substituting in n minus 1. And of course, we can simplify this thing greatly. First, we just rewrite it as a single fraction, and now we're going to have all sorts of cancellation. All n minus 1 copies of 5 down here are going to cancel with 5s up here, and there'll still be 1 5 left over because they're not n minus 1, but n of them. So I'll still have 1 5 left upstairs. And for now, I'll go ahead and keep those factorials where they were. If you're already comfortable with factorials, then you know what to do with these. If you're less than comfortable with them, you might need a minute to figure out what's going on here. But that's easy if you just think about what a factorial means. Downstairs, this is the product of the first n whole numbers. 1 times 2 times 3 times 4, all the way up to times n. Upstairs, this is the product of the first n minus 1 whole numbers. 1 times 2 times 3 times 4, up to n minus 1. So everything up here, every factor there, cancels with a factor down here. But there's still one last one left over down here. There's one n that we didn't get to. So all of that will reduce to 1 over n. If you want to see that more explicitly, if you want to see it written out, you could always rewrite that n factorial as n minus 1 factorial times n. Why is this the same as that? Because the one on the left is the product of the first n whole numbers. On the right, we have the product of the first n minus 1 whole numbers. And then to bring it all the way up to n factorial, we still have to multiply by n. Anyway, n minus 1 factorial cancels with n minus 1 factorial, and we are left with just 5 over n. And actually, in this case as well, the absolute values were unnecessary. Since n is always a positive number to begin with, this whole thing is positive. I'm just going to leave them on there because it does no harm. And after all, we're not interested so much in that thing in and of itself. This is the term-to-predecessor ratio of this guy. So it's related to the notion of a geometric series. That's why we care about term-to-predecessor ratios. Is this thing geometric in the tail where convergence is determined? Well, let's look to see what it looks like in the tail. What happens in the limit? As n goes to infinity, that ratio, of course, goes to 0. Which means that in the limit, every term is effectively nothing compared to its predecessor. That's really rapid vanishing to 0. Which is, of course, what we were saying in the beginning. Exponential growth is really fast, but factorial growth is another story altogether. But what we care about here is the fact that 0, that limit, is less than 1. So by the ratio test, the series converges. In fact, absolutely. All right, so there's your second numerical example with the ratio test. As I said before, our main interest in the ratio test is going to be applications to power series, which are, in fact, our main topic for this video. A power series, as I've said a few times already, is the fancy term for an infinite degree polynomial. Sometimes those polynomials are in powers of x. Sometimes they're in powers of x minus 2 or x minus 5 or something like that. Just like you are used to from Taylor series. Sometimes we center a Taylor series at 0. Sometimes we center it at a, in which case it comes out in powers of x minus a. Let's go ahead and be general here in the video. In the book, I begin by having all our power series centered at 0, but let's just center them at any old number a. A power series centered at a is a series of the form we could describe this way. Expanded out, it would look like this, which should make you feel at home, because Taylor series have this form. The only difference is that in a Taylor series, there's a little extra structure. For example, instead of any old constant, a sub 2, it would have to have a very specific form, something like this, involving derivatives and factorials. But at the end of the day, that's just an example of a constant. So power series are a little more general than Taylor series. Taylor series is a specific type of power series. And although Taylor series are the ones we're ultimately interested in, we learn a lot by enlarging the scope of our attention to the larger class of series. Anyway, the important thing to bear in mind about a power series is that a power series is a function. You have infinitely many choices for what x can be. And if you pop a different value of x into this thing, that value shows up in all of these terms, which just become constants, and we get a different infinite series of constants that comes out. And that infinite series of constants may converge or it may diverge. And one of our main concerns is going to be to figure out which values of x make a given power series converge and which ones make it diverge. As we will see, there are some power series that converge for all real values of x, and others that converge only for certain values of x. Every power series converges at least one point, namely at a, at the point where it's centered. Because if we pop a into every one of these x's all the way down, well, all those x minus a's become zeros, which means that all these terms get wiped out, and instead of an infinite series, well, we just get one term, a sub 0. So of course it converges when x is a. It converges, so to speak, to a sub 0. But that's not the interesting case. We're interested in what happens away from a. Just as when we were talking about Taylor series, if I have some function and I approximate it with, say, a Taylor polynomial, I know that the fit of the polynomial to the function will be perfect at the point where I've centered it. But the interesting question is, what happens when I get away from that point? Does it stay close, or does the polynomial fly away from the function I'm trying to approximate? And as I've hinted a few times, the tool we use to determine where a power series converges, in other words, for what values of x it converges, is this ratio test that we've been talking about. And an example should make this clear. So, determine the values of x for which this power series converges. Now, this is a power series centered at 4, so we know that it converges when x equals 4. That's the trivial solution. I'm going to keep track geometrically of what's going on with a tiny little drawing up here. That's supposed to be the real line, and I know that when x equals 4, I get convergence, so I'm going to put a little green dot there. I'll use green for convergent and red for divergent. And we certainly could just play around with this numerically, put in some different values of x and see what happens. That is normally not a good strategy for doing these kinds of problems, but just to show you what I mean, let me come over here in Scratchwork land for a second and give an example. We could say something like, well, when x is 10, if I put 10 in there, I get 10 minus 4 is 6, so the series becomes this thing. But then I have 6 to the n over 3 to the n. Well, that's 6 over 3 to the n, which I could rewrite as 2 to the n. And now I have a series which obviously diverges by the divergence test. Hence, if I were to go up here on my picture, I would know that when x is 10, the power series diverges. But the problem, of course, is that there are infinitely many real values to check. So I can't just check them all individually one by one. I'm going to need to check many at once. And this is where the ratio test is going to help me. So let's see what that's going to look like in practice. The term-to-predecessor ratio, the key expression for the ratio test, is going to be, in absolute value, this, the general term, over this, its predecessor, which we obtain by changing all the instances of n to n minus 1s. Naturally, this horrifying expression can be simplified by turning this all into one fraction, like this, and then doing some cancellation. First, we look at all these factors of 3. There's one more downstairs than upstairs, so we can cancel everything but that one extra 3, which I can pull through the absolute value as well, since that factor of a third is obviously positive. What does that leave me with? Well, I've got this n squared over n minus 1 squared. So I could rewrite that as n over n minus 1 quantity squared. And come to think of it, this is positive 2. So I can pull it through the absolute value, like so. And what am I left with inside? These powers of x minus 4. I've got n of them upstairs and n minus 1 downstairs. Well, they all cancel out except the one extra one upstairs. So I end up with x minus 4 when all the dust settles. And of course, there's nothing I can do about those absolute values because this quantity could be positive whenever x is greater than 4, or could be negative whenever x is less than 4. But lest we forget, what does this all represent? Oh, good thing I wrote it down. That's the term-to-predecessor ratio in absolute value of this power series. Why do we care about the term-to-predecessor ratio? Because its limit, as n goes to infinity, tells me something about the series. Okay, well, what happens to this expression as n goes to infinity? Well, the third just sits there. The x minus 4 in absolute value just sits there. The only place n shows up is in this factor. And as n goes to infinity, this fraction goes to 1, which means this whole factor goes to 1. So let me write that down. This goes to 1/3 absolute value of x minus 4 as n goes to infinity. Unlike those previous cases where we used the ratio test, this was not just a single numerical series, so we don't end up with just a number, 2/3 or 7 or whatever here. I have this expression which itself is a function of x, because of course for different input values of x for this power series, I'm going to get a different numerical series out, and therefore the term-to-predecessor ratio will be different. In particular, it will depend on the value of x we put in. But what does the ratio test tell me about this limit? It tells me the series will converge absolutely when this is less than 1. So let me write that down. So by the ratio test, the power series will converge absolutely when this expression is less than 1. Okay, great. So for any value of x that satisfies this, I know the power series will converge. But which values of x satisfy it? Well, that's easier to see if I isolate the absolute value on one side of the inequality. So multiply both sides by 3 so that we get this. That's much easier to understand. You just have to remember something important about absolute values. How do you interpret something like a minus b in absolute value? Well, that just refers to the distance between a and b on the number line. I'll leave it to you to verify that for yourself if you're not already familiar with it. But in our case, that's telling us that the series is going to converge when the distance between x and 4 is less than 3. Well, we can see what that is. I mean, here's 4 on the number line. If the distance between x and 4 has to be less than 3, then x can go out 3 units this way and 3 units that way, which takes us out to 7 in this direction and 1 in that direction. So let me write that down here. X is between 1 and 7. Or if I put that up on my official picture, I'll have convergence anywhere between those 2 points. I'll leave those 2 points hollow because I don't know what happens at those points yet, but I know that everywhere between them I get convergence. Ah, now that is nice, because instead of just getting an isolated point here or there, I've got a whole interval like that, infinitely many points in there. And actually, the ratio test tells me something else for free. It tells me that the power series converges absolutely when this thing was less than 1. But what happens when this thing is greater than 1? In that case, the ratio test tells me the series diverges. I'm just going to put this in scratch work. But if the series diverges when this happens, well, that's the same condition as this, just multiplying both sides by 3. And how do I read that? That's all x for which x and 4 are separated by a distance of greater than 3. So that's everything beyond 7 and beyond 1 in the respective directions. So I know that we get divergence everything beyond 7 and everything to the left of 1. And in fact, this sort of thing happens for every power series. We will always get convergence in some interval centered at the center of the power series. It might be a finite interval like this one, which stretches from 1 to 7, or it could be an infinite interval that goes from minus infinity to infinity, but it's always going to be this interval symmetrically arranged around the value a, the center of the power series. So in practice, when we write something up like this, we give our work to show where the series converges, but we don't even bother repeating this kind of argument for where it diverges, because we know it's going to diverge everywhere outside of that so-called interval of convergence. And in the book, I give a formal proof of why that is so. Anyway, we're not quite done. We know that our power series converges for all real numbers greater than 1 and less than 7, and diverges for all real numbers greater than 7, and diverges for all numbers less than 1. But what happens at 1 and 7? What happens at the endpoints of my interval of convergence? I have to check those separately, and this is just part of the game of figuring out where a power series converges. And I've run out of space, so I'm going to have to move this up like so. And now we still need to test the endpoints. When x is 7, the power series takes this form, where we've put in 7 for x. Well, 7 minus 4, of course, is 3, and this 3 to the n and this 3 to the n cancel, leaving us with a series which diverges by the divergence test, since the general term obviously does not go to 0. It blows up to infinity, in fact. Okay, so we know that at this endpoint, we actually have divergence. What about when x equals 1 at this other endpoint? Well, then the series takes this form, where instead of x, we have a 1. And so we end up with 1 minus 4, which is minus 3. But to get the cancellation here, I'll note that the minus 3 to the n can be written as minus 1 to the n times 3 to the n, which means that these two factors of 3 to the n, which means that these 3 to the n's cancel, leaving us with this series, which again has a general term that does not vanish. In magnitude, it blows up to infinity, and its sign keeps flip-flopping from positive to negative, so which diverges by the divergence test. And that means that if we come up to this other endpoint, we know that we get divergence there as well. And now we know exactly how this power series behaves, at least with respect to convergence status, everywhere on the real line. So let's sum that up and introduce some vocabulary that I've already used in passing. Thus, the interval of convergence for this power series is 1 to 7. And I'm guessing you probably know this notation, but just in case you don't, the rounded parentheses indicate that the endpoint is not included. So not including 1 and not including 7. If you want to include an endpoint, you use square brackets. We'll see an example of that shortly. And that's the basic way you solve one of these problems. Given a power series, if you want to find out where it converges, and by the way, now that we know this vocabulary, interval of convergence, a question like this would probably be posed, find the interval of convergence for the power series, such and such. But anyway, we do a ratio test, which means setting up the term-to-predecessor ratio, taking its limit as n goes to infinity, figuring out where that's going to be less than 1. That tells me where it's going to converge. I'll have some endpoints that I'll need to evaluate, unless, of course, it converges everywhere, which is possible. But in general, I'll have endpoints that I need to evaluate, write everything up nicely, tell me the interval of convergence at the end, and we're done. There's a fair amount going on here. None of it's terribly complicated, but you do need to keep it organized. Let's do another 2 examples of finding the interval of convergence of a power series. This time, let's go back to Taylor series. Find the interval of convergence of the Maclaurin series for e to the x. And remember from the book, Maclaurin series is just a name for a Taylor series centered at 0. So in this case, we are talking about the usual series for e to the x, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. It's a Taylor series. That's a special type of power series. That means it's a function. And for different values of x that we could pop in here into this series, we'll get different numerical series out. Some will converge, and it could be the case that some diverge. Let's find out. We know we always start this process with a ratio test. The term-to-predecessor ratio is, in absolute value, well, here's the general term of the series. Its predecessor is obtained by turning all these n's into n minus 1s, like this. Let's clean this mess up by putting it all into one fraction, and now taking care of the cancellation. Let's deal with these factorials first. We saw an expression like this earlier. The top is the product of all the whole numbers up to n minus 1. The bottom is the product of all whole numbers up to n. So everything up to n minus 1 cancels with a factor up here, and we're left with just n down below. So we're going to have that. And now for the x's. We have n minus 1 copies downstairs and n upstairs, so we end up with just 1 upstairs. So our expression reduces to that. And if you want, you could even pull the 1 over n out of the absolute value, because that will always be a positive factor. X, of course, could be positive or negative, so it has to stay within. All right, so what is this? This is the term-to-predecessor ratio. Why do we care about that? because we want to take its limit as n goes to infinity. Now again, we haven't specified what x is. X could be any real number, but whatever x is, whether it's 0 or 5 or negative 3,000 or pi plus e divided by the square root of 2, whatever constant that may be, when we take the limit as n goes to infinity of this expression, that constant, that value of x, just sits there while the denominator blows up. So this entire expression vanishes. And 0, of course, is less than 1, and this holds for all real values of x. So for all real x, this series converges. Absolutely, in fact. If I were to draw my little picture of the real line, it would be very boring. It's centered at 0 and it converges everywhere. It's just a green line. Thus, the interval of convergence for this series is from minus infinity to infinity. We don't have to check any endpoints this time because there are no endpoints. It just covers the entire line. Now this is very interesting because this takes us back to the very beginning of the chapter when we looked at the Taylor polynomials for e to the x centered at 0 and compared them to Taylor polynomials for other functions like 1 over 1 minus x. And what was notable about the Taylor polynomials for e to the x was that as we kept increasing the degree, the interval over which the approximation was good seemed to cover more and more and more of the real line. This now makes more intuitive sense since we have now seen that the Taylor series for e to the x converges everywhere on the real line and not just on some finite interval. And that is that. Let's do our third and last example. Find the interval of convergence of this power series. Written out, that would be 1 plus a third x plus a fifth x squared, and so on. We don't need to have it written out, but sometimes it's nice just to see what it looks like. All right, find the interval of convergence, meaning we know that for certain values of x, this power series will converge, and those values of x will comprise some interval on the real line. Find that interval. We will begin, as always, with the ratio test. So, the term-to-predecessor ratio is, in absolute value, well, here's the general term. We need to be a little careful with the predecessor. The top, of course, is x to the n minus 1 power, but the bottom is something I've seen students screw up too many times for me to let it pass without warning. I've seen people write here 2n. That is not correct. It's not correct because you get to the predecessor by letting the index be n minus 1. Not from subtracting 1 from whatever is there already. In other words, 2n plus 1 should be 2 times the quantity n minus 1 plus 1, which shakes down to something other than just 2n. Everything else stays as is, but this simplifies to 2n minus 2 plus 1, which is 2n minus 1. So be careful not to be the one to make that mistake there. Anyway, we can simplify this considerably. The 2n minus 1 comes upstairs and sits above the 2n plus 1, so we have this stuff. This x to the n minus 1 comes downstairs, and all gets canceled out with everything up here, except one x survives on top, so we end up with this. And I think this is a little easier to work with intuitively if we separate it out into two factors. The absolute value of a product is the product of the absolute values, so I can rewrite that as this. All right, why were we doing all these computations? Because this is the term-to-predecessor ratio, like when we're looking at a geometric series. Our series is not geometric, but maybe it becomes geometric in the tail, or something like it. Well, what happens in the tail? What happens as n goes to infinity? This whole expression just goes to the absolute value of x, because this left factor, as n goes to infinity, goes to 1, because for large values of n, these constants can be neglected, and we end up with something of the form 2n over 2n, which is, of course, 1. All right, so what does this tell us? Well, the ratio test tells me that the power series is going to converge when this is less than 1. So let's write that down. Thus, by the ratio test, the power series converges when absolute value of x is less than 1. So now I can think about this geometrically. The series is centered at 0, and absolute value of x less than 1, that means x could be anything between minus 1 and 1. We know that so long as it's in that interval, I don't know what happens at the endpoints, but so long as it's in that interval, I get convergence. And outside of that interval, I'm going to get a divergent series. Oh, by the way, a little terminology in passing. I use it in the book, but I don't think I've used it in this video yet. This length right here from the point where the power series is centered to the endpoint of the interval. That length is called the radius of convergence. So the radius of convergence in this case would just be 1. Now we need to check the endpoints of this interval. When x equals 1, at this right endpoint, the series becomes this. Well, what do we know about the convergence status of this series? By now you're an expert on this sort of thing. What does the general term look like in the tail? Well, the 1 can be neglected, so the general term looks like 1 over 2n, and we know that the series 1 over 2n stands or falls with 1 over n, because a constant multiple doesn't change anything. And this is the harmonic series, which diverges. So we can see what's going to happen to this one. It's going to diverge. But how are we going to write that up carefully? Well, we're going to use a limit comparison test. So let's write that down. The series becomes this, which diverges, why? By limit comparison with what? This series. Well, why does that diverge? Because it's the harmonic series, which everyone knows diverges. Okay, but why does the limit comparison test apply? Since if I take the ratio of the general terms of those two series, which of course simplifies to n over 2n plus 1, I find that in the limit, it goes to a constant 1/2, which is not 0. So the limit comparison test does indeed apply. Good. So we know that in my picture up here, at 1, we get divergence. Well, that just leaves the case when x is minus 1 at this left endpoint. There, the series becomes this. Well, what kind of series is that? It's like the one we just looked at, except we have this minus 1 to the n. What is that doing? That's making these terms change sign each time we go out one step further. In other words, this is an alternating series. Well, those are easy to test for convergence. We just use Leibniz's test. Think about the magnitudes of these terms, which are just 1 over 2n plus 1. Those obviously get smaller and smaller with each step as n gets larger. In other words, they are vanishing monotonically. Thus, we know that this series converges. So the power series becomes this, which converges. Why? By Leibniz's test for alternating series. Well, why does that apply? Since the magnitudes of the terms, which have this form, vanish monotonically. So that means, in terms of my picture over here, I get convergence, a green dot at the left endpoint. And now I know more than the fact that the radius of convergence is 1. I know the actual interval of convergence. Thus, the interval of convergence is the interval from -1 to 1, where the -1 is included, hence my square bracket, but the 1 is not, hence my round parenthesis. And that is the long and short of it. And you have now met all the major convergence tests. There are others, including a couple of other reasonably common ones that I put in the exercise set of this section of the book. There's one called the root test, which is related to the ratio test, and there's one called the integral test, which you've essentially used already, we just didn't give it a name, and they're worth spending a little time with. And there are more exotic tests beyond these. But you've hit the major ones. You now know what a power series is, and that Taylor series are just special power series with a little extra structure on their coefficients. So I think it's time for you to stop watching this thing and get to work on the homework problems if you haven't started them already. Bonsoir.